I really appreciate you taking your time to come over here and help out with this today.
Oh, no problem at all. I enjoy thinking about numbers, but I am missing my game on TV.
Well, maybe it'll be worth it.
All right, maybe. Oh, is that Sue? I'll get it.
I'll get it. Hey,
Frank.
hi, Sue, come on in.
Well, Sue,
Hi.
you finally made it, huh?
Yeah, look, I'm sorry I'm late, but my husband couldn't be home after all, so I had to take the kids to their grandparents, and you know.
No, well, now, look, I don't want to cause you any difficulty.
Oh, no, no problem at all.
You sure?
I'm sure.
Okay. Well, listen, this is what I've got on my mind. Now, we're just about out of class time, and we really do need to cover some more algebra and geometry, so I'm hoping that I can talk you two into being, well, sort of like tutors for the rest of the class.
Tutors?
Yeah, you both have real good number sense, and I'll work with you closely.
Well, I'm flattered, and I'm willing to give it a try.
Sure, why not?
Yeah? Okay, well, good. Now, you remember these packets?
Yeah, and I see you brought the charts, too.
Right. Now, this is our curriculum. Well, what do you think?
Well, they've been pretty clear so far,
Yeah?
right?
Well, what we'll do then is divide the class up into small groups, and then you'll each work with certain people.
Okay, where do we begin?
Well, Sue, what do you think is the most important thing about understanding algebra?
Well, balance, we've talked about that some.
Yeah, and I think the idea that letters can be treated as numbers is important,
Yeah.
especially since you can make them anything you want them to be. And they can be added or subtracted, multiplied or divided, and you don't have to know the value.
Right, and that values can be substituted for the letters if they are equivalent.
Oh, and the order in which operations are performed is important.
Right.
Oh, I know, it's command, right?
Right, yes, I just saw that here. Here it is. Simplify the parentheses, compute powers and roots, multiply or divide, add or subtract, divide the denominator.
Right. Now, I think if you start with a simple example of that, you can get the whole story pretty quickly. Well, here. Now, Sue, write this down, all right?
Okay, thanks.
3 plus 2 times 4.
Okay, well, if we did it in the order you said in numbers, that would be 3 plus 2 is 5 times 4 is 20. I know that's not right.
No, you have to multiply first, so it would be 2 times 4 is 8, plus 3 is 11.
Oh.
That's right.
Can we do one that uses the whole command?
Well, you rarely have a problem that uses them all. You know, you just tell your folks that you start with the operation highest in the order.
Well, you know, all this makes sense, but you have to follow a set plan or they're going to get messed up.
That's right. That's right. Well, now look, here, you'll hardly ever see a problem more complex than this.
Oh, well, I think I can work through this. It would be parentheses first, 2 here, 2 is a power inside parentheses, and 16. And below the line, it would be 3. So now we can multiply from left to right. That would be 6 times 16 equals 96. And that's above the line of 2 times 3, which is 6, and divide the denominator, that would be 16.
Marvelous. Now, if everyone can do that, we're in great shape.
Well, I don't know. Parentheses seem to scare some people.
Well, yes, they do. But, you know, if they'll just think of them as a package that says, open me first, they'll be okay. All right.
You know, I was just noticing here in this worksheet, that I think one of the problems that's really going to give them trouble is the one that says to compute the square root.
Oh, that's probably true. And the first hard thing about it is the definition.
Oh, it sure is. I'll read it here. Extracting the square root of a number means to find a number that when multiplied by itself gives the original number.
Well, that's not real clear, is it?
No, but it's easier to see from the example.
Let's see.
Well, sure, when you say that 5 is the square root of 25, I mean, that's pretty clear. 5 times 5 is 25. But what about bigger numbers?
Well, I think the best way is to use the averaging system because you can get an estimated answer very quickly. Let's just work through this example and see what happens.
You know, I think the secret of that, too, is to try to get a good estimate the first time out.
That's exactly right, because if your estimate is close enough, then it doesn't matter whether the answer is too big or too small.
Yeah, well...
Let's do this one here. Find the square root of 576.
Okay, will you talk me through that then?
Sure.
Okay.
Okay. The first thing we have to do is to estimate a number That's close. So 40 would be too high. That's 1,600.
Well, you know, even if the answer weren't right in front of my face, I'd know the answer was between 20 and 30.
All right, so, well, let's just divide 576 by 20.
Okay.
Okay, and that would give you a quotient of 28, right? And ignore the remainder.
Right.
Now you have to add 20 to the quotient, 28.
Okay.
That would be 48. Now you have to average that.
So that divided by 2.
Right, 48 divided by 2 is 24. Now 24 times 24 is 576.
Okay, so then the square root of 576 is 24.
Right.
Right.
Okay.
Now suppose the larger the number, the harder it is to get a good estimation.
Well, sometimes you can use the standard method.
Let's do another one using the averaging method.
Okay.
Okay.
Find the square root of 2,116.
Okay, well, I can tell right off that the answer is going to be between 40 and 50, maybe 45?
Great.
Oh,
Great.
okay.
Now divide and then average the divisor and the quotient.
Okay, 45 divided by 116 is 47. 47 plus 45 equals 92. And that averages to be 46.
And 46 times 46 looks like it's going to do it.
Yeah, look right here.
There it is.
Well,
Yeah.
that's great. You guys caught on to that real quick.
Say, Sue, did you get that challenge question on that last handout?
You mean the simultaneous equation?
Is that what they call
You
it?
know, I looked at it, but I haven't figured it out yet. Have you?
Well, I did, but I cheated.
You cheated. How can you cheat?
Trial and error.
Hey, trial and error is a time-honored mathematical technique. You want to read the problem to us?
Well, sure. I've got it right here. 2z plus y equals 19, or stated in another way, z plus y equals 12. Find the value of z and y.
Okay, so what do you do?
Okay, well, I worked it out over here. It's, well, since the operation in the problem says to add, I did the inverse and subtracted the z plus y from this side and the 12 from this side. Then I substituted the 7 for that z, and then I had to multiply the 7 by 2 because it's 2z. So I added that 14 to y, which equals 19. Then I subtracted 14 from each side, and that left y on one side and 5 on the other. So z equals 7 and y equals 5.
Wait a minute. I don't understand how that fits the rule of subtracting the same thing from both sides.
Well, now look at it again, Sue. As that's written there, doesn't z plus y, isn't that the same thing as 12?
Oh, okay. So when you subtract the z plus y is the same as subtracting the 12 from this side,
Right.
even if you don't know the value of the letters yet.
That's it. These two expressions are the same.
Simultaneous equations are a very good way to practice inverse operations and substitution.
Good.
You know, if we can just get these ideas across to our crews and possibly powers and roots, then I think... That must be the pizza. But listen, before I get it, I want you to take a look at this, all right?
Hey, that's that fish problem I told in class the
Oh,
other
now
night.
I can't believe you went to that much trouble. Why did you go and do that?
Why do you think?
Well, it looks good to me.
Well, now, this is a very representative problem, and I want to use it again in class, all right? You're going to be seeing this again. Sue, what do you want to drink?
Do you have some tab?
Yeah.
Okay.
Hello again. Let's go over some of the things you saw and heard in this scene. Todd points out that when letters are used in algebra to represent an unknown quantity, they can be treated like numbers even if you don't know their value. They can be added, subtracted, multiplied, and divided. They can be substituted for numbers, or numbers can be substituted for them as long as everything stays in balance. The sequence in which operations are done in an algebra problem is very important. In this problem, since multiplication is a higher priority than addition, the 2 is multiplied by 4 before the 3 is added. The answer to this problem is 11. Remember, too, that the operations in the parentheses come before anything else. They are a package that says, "Open me first." In this example, then, 2 is added to 4 before it is multiplied by 6. This must be so because, as it is written, we must be certain that the 6 is multiplied by everything in the parentheses. Frank had Sue and Todd use the averaging method to find the square root of a number. Let's review that method and find the square root of 1764. The first step is to estimate or guess a round number that looks close to the right answer. Let's try 45. Step 2 is divide your guess into the number you're finding the square root of. Next, you ignore the remainder, then add the quotient and the divisor and find the average. The final step is to multiply this average times itself. If your estimate is good, the answer will be the original number, and you'll have found the square root. In this case, the square root of 1764 is 42. Of course, it's always possible that you'll have to try more than one estimate, and if you prefer, you can practice and use the traditional method of finding the square root, which is in your workbook. Simultaneous equations were mentioned briefly. Suppose at your neighborhood store you could get 2 pears and 1 apple for 19 cents, or 1 pear plus 1 apple for 12 cents. What would be the cost of a half dozen apples? Written algebraically, it looks like this. If we do what Todd did and we subtract, we find that each pear costs 7 cents. Therefore, apples must cost 5 cents, because that's the only thing you can add to 7 to get 12. If 1 apple costs a nickel and you want 6, then the apples would cost 30 cents a half dozen. Well, let's find our friends and see what else they are learning.
You know, if we don't get this settled pretty soon, we're going to have to pay rent on this
Man,
spot.
I'm getting there. Let's go over it one more time. Okay, the order in which you do things is important,
It's
right?
critical.
Okay, explain it one more time and then give me an example.
All right, let's, I'll tell you what, we'll substitute a value and simplify it. Write this down.
All right.
C plus EF.
Okay.
C is 7,
Mm-hmm.
E is 9,
Mm-hmm.
and F is 11. Got that?
Okay, yeah. First of all, we substitute, which gives 7 plus 9 times 11, EF with no sign between them. That just means to multiply.
Good.
And that would be 7 plus 99 equals 106.
Good,
That-
good.
that-
Now
that
remember,
wasn't hard. I
don't
could do
take
that,
out the
yeah.
winning team. Repeat after me. Scamad.
Do I have to? Oh, okay. Scamad.
Scamad. All right, let's try another one. Here,
Okay.
I'll give you one here. Let's try, we'll say 6 times 2 plus 4 minus 2 times 4. Now, see what you can do
Okay. First of all, I simplify the parentheses.
Right.
So 2 plus 4, that'd be 6. So we have 6 times 6 minus 2 times 4. We multiply 36 minus 8, 28.
there. That's good. That's
Got that one,
good. Now
too.
you're ready for the big time. All right, we'll try something else. Try
boy,
this.
it's a big time. All right.
2z
Uh-huh.
plus bc squared.
Okay.
Okay, now let me give you the variables.
All right.
Z is 2,
Okay.
B equals 3, C equals 4. See what you can do. with that.
Okay. First, I substitute. It would give me 2 times 2 plus 3 times 4 squared.
Right.
Then scamad.
Scamad.
Now, there are no parentheses, so I go right to the powers. This little number here, that's the next one. That 2, that means 4 times itself. So this would be 2 times 2 plus 3 times 4 times itself is 16. Okay, the next step is to multiply. That would be 4 plus 3 times 6, 48. And then we add, and there are no denominators, so it would be 52. I
Buddy,
think.
I'm impressed.
Is that right?
I don't know.
What kind of a teacher are you, anyway?
I'm no teacher. I'm a
I
paint
know.
store clerk.
Hey,
Glad you're
Martha.
here. Been doing the same thing we've been doing, huh?
Yeah, how's it going with you all?
Very well.
well. I'm enjoying this.
I sure hope Sue is more patient than Todd. What a grouch.
Grouch I am not. I'm just thorough. That's all.
May we sit down,
Oh,
guys?
yes, ladies,
Thank
forgive
you.
us, of course.
What is all this? What is this?
What have you been eating?
We've been here so long, we've had a little bit of everything.
Ladies, would you like something? I'll go get it for you.
Yes, but make mine diet, please.
Just anything,
Yes,
Doc?
something soda.
How about
Martha?
some iced tea?
Okay, I'll be right back.
Wait a second, I'll
wait
give
a
you some
minute.
change.
Oh, no, this is on me.
Oh, thank you, Todd.
Todd. So, what have you been doing?
We have been working on the order of operation in simplifying an equation.
Yeah, we did some of that.
We've been studying algebra terms.
Oh, yeah, we did that too. Pretty boring.
Well, it's not real exciting.
But we gotta use those terms to communicate.
Yeah, I guess so, but it isn't too interesting. Afraid.
Listen, Sue and I have developed this word association game, which is pretty interesting. Want to try it?
How does it work?
Well, I say a word, and then you say the first word that pops into your head.
Okay, why not? Hit me.
Formula.
Diapers.
Diapers?
Yeah, sure.
Bill!
Hey, if you had little kids running around the house, it would make sense to you.
We are looking
yes.
for math terms. Now quit kidding around.
Oh, okay. Give me another one. Give me another one.
Do formula first.
All right. Pi r squared.
Hey, that's
Yeah.
good.
Exponent.
Power.
Variable.
XYZ.
Constant.
Number.
Root.
Beer.
Root beer?
Ice cream.
Bill, I give up on you.
Hey, what's going on here?
Oh, Bill's just being Bill.
Oh,
Kidding
Martha
around.
had good intentions, though. They were playing a word association game with algebra words.
And Bill blew it.
Yeah, sure
Well,
did.
you know what happens to my attention span when I'm drinking this root beer?
Hey, why don't we do it like that password game?
Oh, I sort of remember that. Wait a second, how does that go?
Well, you know, I'll give a one-word clue. You give a one-word answer until you get the word.
I'll try it with you.
Okay, letter.
X.
Value.
Unknown.
Changes.
Equations.
Substitute.
Variable.
That's it.
How
Okay.
did you get that?
Well, a variable is a letter and an unknown, and it changes and can be substituted in equations.
I see.
Yeah.
Let me try one, Todd.
Okay, number.
25.
Unchanging.
Constant.
That's it.
That's quick, Martha.
That's right on the ball.
What's
You
that?
try one, Bill.
If you insist.
Yes.
Okay, number.
Numeral.
Exponent.
Multiplication.
Base.
Square.
Fourth.
Power.
That's
Good
it.
work,
Yeah.
Bill. But I think we ought to try something a little more productive,
Like what?
like a square root.
Oh, good. That ought to put us to sleep.
Oh.
Well, you know, Sue knows this method of averaging to find a square root, and I got pretty good at it. In fact, I'll even race you guys.
What do you mean, race?
I mean, I think I'm so good at this that I can find the square root of any number faster than you can.
Oh, you can you?
Mhm.
Well, put your money where your mouth is.
Okay. Sue, you be the judge, okay? Give us a problem.
I'll find the square root of 2,704.
Go get them, Todd.
Got it.
Martha's the winner.
Well, wait a minute. Inquiry. You two must have set this up. That was impossible.
No, Martha
Yeah.
actually computed the square root at the same time you and Todd did.
I don't believe it. How'd you
Yes.
do it? How'd you do it?
Should I show him, Sue?
Yes.
Oh, well, why not?
Okay, here's the secret formula. Ta-da!
Should have known it.
Later, it's
You,
always a
and we trusted you
Oh,
two.
well, yes.
Never again.
Some of the terms that were used during the games our friends were playing are in your workbook. Each chapter of the book has a vocabulary section to help you learn the words that will be useful to you. Bill simplified this statement to prove a simple problem can be used to solve much more complicated ones. 6 times the quantity, 2 plus 4, minus 2 times 4. This is the way he did it. Parentheses first, 2 plus 4 equals 6. There are no powers or roots, so next comes multiplication. 6 times 6 and 2 times 4. 36 and 8. Be sure to memorize the order of operations for this type of problem. Simplify the parentheses, compute powers and roots, multiply and divide, Add and subtract. Divide the denominator. Schemad. When you do, you can use the same plan to solve much more complicated problems. Look at this one. See what I mean? They almost solve themselves. In the last part of this scene, you heard about powers and roots. Power means a number multiplied by itself. The exponent, that little number, tells you how many times to do it. 4 to the second power, or square, means 4 times 4. 4 to the power of 3 means 4 times 4 times 4, and so forth. Let's return now and see what our foursome is up to.
What a wonderful evening.
Yes, it
Goodness, why don't we walk to class?
And that's a good idea.
Wait a minute, are you sure our cars will be all right here?
Oh, yeah, I leave mine parked here all the time. Hey, instead of walking, why don't we run?
He's kidding. Tell me he's kidding.
He's not kidding, but I would be if I said yes.
Well, I am going to run. I'll meet you all in the park, okay?
All right, see you at the park. What a man.
It is a beautiful evening tonight.
Yes, it is.
What do you think Frank's going to give us in class today?
Oh, probably some more about formulas and substitutions and whatever, you know.
I'm pretty worried about learning all those formulas.
Hey, you'll do fine. You've done formulas before. Remember, I pert.
Do I? All those interest problems in that computer
Well,
program?
it's just the same thing. You just substitute the values in the right places in the formula.
I know. You said it before, but...
Well, you won't have any problem with it. Look at this. That's the old 97 puffing down the
Hey,
track.
what happened to you guys? When you didn't show up, I ran around the park 4 times.
We were outside breathing fresh air.
Well, fitness nut.
You know, back to what we were talking about, Martha?
Yeah?
When you're using formulas, there's always at least one thing missing. And that's what you're looking for.
Well, I know that, but look at these sheets. I mean, they're getting really complicated. Look at this one. It says c squared equals a squared plus b squared. Now, I know that's supposed to tell me something about the sides of a triangle, but beyond that, I don't have a pig in a pickle barrel.
That's what I was talking about before. You'll always know 2 of the values. If you knew all the others, there'd be no point in doing it. You'd already have the answer.
And then it's just a matter of just substituting the values in the right spot in the formula and then carrying on with the operation.
Okay, show me, using this formula here.
Okay, now look. This is a right triangle. Now, all right triangles have a hypotenuse.
This.
Right, that's that line across from the right angle. Now, if you just forget about the geometry and concentrate on the algebra, we can make a general statement about all 3 possibilities.
Why are there 3 possibilities?
Because a triangle has 3 sides. In each case, you know the length of 2 sides, but not the other. That's why I think geometry is easier if you know the algebra.
Yeah.
Well, this says c squared equals a squared plus b squared. And then it says that there are 25 little squares on the c side, right?
Right.
16 little squares on the a side and 9 little squares on the b side. Now you add 16 little squares plus 9 little squares, you get 25 little squares. So the math works out, but what does it mean?
You're starting to sound like Bill.
Just a minute, Sue. Let me have that piece of paper.
Okay.
I will show you what it means. It means that if you know that side and know that side, you square them, add them, and then you know that side.
No. You only know how many
No,
squares can be drawn on that side. Now, if you
no.
want to find the length of that line, you're going to have to compute square root.
That's right. See here, we have 25 squares. If you want to know the length, you have to find the square root of 25.
Right. You see, that's why that little symbol's there.
This?
Right. It means find the square root of whatever is written inside of it.
Okay, but what's the square root?
The square root of a number is a number which, multiplied by itself, gives the original number.
Right. And fortunately, we're looking for the square root of 25, which is easy. 5 times 5 is 25.
So what you're trying to tell me is that the length of c is really 5, not 25.
Right. And that's what Frank means when he says solving for c. C is the unknown.
And this is to find C. You know A and B, and we're looking for C.
Well, what if we knew what c was, and then we were trying to find one of the other sides?
Inverse operations.
With this basic formula and what we know about literal equations, you can find the length of either of the other two sides.
Yeah, you see there, B?
You mean this here?
Right. B is the unknown.
And here, A is the unknown we're solving for.
And that is what a formula is for.
Yeah.
I think I'm beginning to understand.
Well, all right.
I think it's about time for class, isn't it?
Yeah, I guess so.
So,
I think.
Pythagoras and his famous theorem will keep coming up in this TV series. Let's see what that formula, dreamed up 25 centuries ago, is all about. Here is the classic picture of the Pythagorean theorem. Pythagoras discovered that if a square is constructed on all three sides of a right triangle, the area of the square on the hypotenuse, the longest side, is equal to the combined areas of the other two squares. In this scene, the formula c squared equals a squared plus b squared was treated as a literal equation, just letters. They didn't actually compute the sides of any particular triangle. Instead, the formula works for finding the length of the side for any right triangle. That's a major value of algebra. It's possible to talk about answers in general. Here is one more look at the formulas. And as Sue pointed out, there's still another step if you're looking for the length of a certain line. In that case, you must find the square root, as these examples show. We will return to the Pythagorean theorem in later programs, so join us next time.